Okay guys, welcome to our video on energy and thermochemistry. Um, so we've probably talked about this a couple of times, but thermochemistry is going to be the relationship between chemical reactions, the energy that's involved, and heat produced from that reaction. So primarily we are looking at energy and heat. So both of those are going to appear in everything that we do, and as we talk through this uh, video on energy, you'll see those two terms pop up a whole bunch. So heat is the energy transferred from a hotter object to a colder one. Generally this comes up as Q in equations. You can also figure it out from delta H, which is entropy, and sorry, enthalpy, not entropy, enthalpy, but we'll talk about that further into thermochem. And then energy is the capacity to do work or transfer heat, and in this case it's going to be capital E in all of our equations. So moving on from there, types of energy. There's potential energy and kinetic energy. Potential energy is going to be the energy of something's position. So a boulder on a cliff, an electron in a magnetic field or near a proton, or simply just the state of matter. So ice versus liquid water versus steam. They each have more potential energy based off of their state. So kinetic energy is energy solely through motion. And you can see the equation there is the physics way of looking at it, using momentum and velocity, or mass and velocity. And you can also look at it in terms of momentum, but it's just the energy of motion. Units for energy, generally we look at things in terms of joules. So joules, you can see the unit there. An alternate unit for joules is going to be Newton meters. And so those are the two general units for joules you see. So kilograms times meters squared divided by seconds squared, or Newton meters. They're the same thing. A calorie is 4.184 joules, and then a kilocalorie is 1,000 calories. It's with a capital letter C. These here are nutritional calories. So anytime you see calories on a food label, these are the kind of calories you're seeing. So there's actually 1,000 calories in each single calorie on a nutrition label. And since you guys are supposed to have about 2,500 some odd nutritional calories a day, that's about 2.5 million chemistry calories. It's a lot of energy. Two other terms that you guys are going to see a lot in this is going to be the word system and surroundings. So system is essentially the chemical reaction itself. It's the reactants and products and anything involved with them. So it only really is the reaction itself. It does not necessarily include anything around it unless it happens to be in a liquid environment or if oxygen somehow involved in the reaction. It's just the reaction itself. Surrounding is everything else, including the glass container you're doing it in. So if you're doing this all in a flask, you assume that the glass of the flask itself is considered the surroundings. So whether or not the surroundings get involved in the problem just depends on the type of problem. Most of the time we assume a closed system. So we assume that the reaction is proceeding without any influence from the surroundings, the things around it. Okay, so this takes us to the relationship between work and energy. So energy is used to cause an object to move. So if you think about physics, that's applying a force to it, and you've now applied some force and moved it some distance, which is work. Work is applying energy to any mechanical system to cause some sort of motion. So in this particular case, again, that's the physics equation, so work equals force times distance. We will look at work in a different way, but it's the same idea, the ability to perform some sort of task. So going back to the Maxwell-Boltzmann distributions that we've seen from previous units, again, work is going to be work is going to be energy that is used to produce something. So the more energy you have, in this case, we have 3 different things at different temperatures. That means that the higher blue line here has, if we were to say, an activation point, that means it has more particles that are capable of doing the work required than the green line or the red line in this case. So work and energy are related. The more energy you have, the more work you can potentially do. So the blue gas here, since it's a higher temperature, has more work potential than the red or the green in this case. And that takes us to the first law of thermodynamics. There are 3 total laws for thermodynamics. We'll focus mostly on the first 2. First law of thermodynamics basically says energy is conserved. There's no way in any system to produce more energy at the out than you have at the input. In other words, you cannot get more energy out of something than you put into it originally, or that was involved in originally. So that means perpetual motion is out, free energy is out. You can only get as much out of it as the amount of energy that was already in the system and how much energy you put into the system. This leads us to talking about endo and exothermic. So if a system absorbs heat, we are calling this a endothermic process. So that's when something gets cold. Happens sometimes when you dissolve salts in water. The system will get cold because it's pulling in energy from the surroundings. So this is talking about how the system is interacting with its surroundings. Endothermic means the system is absorbing heat from the surroundings and everything in the surrounding is getting colder. We call this a positive process. So anytime something is endothermic, then the value of energy is going to be positive. And then anytime something is exothermic, because it's releasing heat, this is going to be a negative process. It's going to evolve heat and give it to the system. It's going to give it to the surroundings, so the system is losing energy. Okay. This is kind of what I just talked about on the last slide, but anytime a system releases heat, it does work, so that also includes performing work of some kind. There's a negative value associated with that. And the change in energy is going to equal Q, which is heat. Let's try rewriting that here. So Q is heat, and then W is going to be work. So the total energy change in a system is going to be dependent on how much heat is involved and how much work is involved. Releasing heat or performing work of any kind is negative value. Absorbing heat or having work performed on the system is going to be a positive value. So this problem is mostly just keeping track of whether or not heat is coming or going, or work is being performed or affecting the system in some way. So let's see how this works in practice. So in this case, we are calculating the change in energy of the system. So the system absorbs 77.5 kilojoules of heat while doing 63.5 kilojoules of work on the surroundings. So it is absorbing heat, so that makes this value right here positive. And since it is performing work, this is going to be a negative value. So then we just plug this all into that equation. So try not to look at like an A here. Delta E is going to equal our positive heat value minus the negative work that was produced. So the total change in energy in this system is a positive 14 kilojoules. Really the only two big caveats to this equation is making sure that your signs are correct, and also making sure that both Q and W have the same unit. They either both need to be kilojoules or both joules. So depending on the problem, make sure that if one value is in joules and one value is in kilojoules, you do that conversion. And because this is a positive energy change, that means it's endothermic. It is absorbing more heat from the surroundings than it is performing work. So one other problem to look at here, so looking at what the problem tells us, it says that the internal energy of this whole system is increased by 300 joules, while 75 joules of expansion work is done. And we haven't really talked about what expansion work is, but we will talk about that on the next slide. The big thing from this is that this is work. So that's what we're going to focus on, is we have a work value and we have internal energy. Internal energy is delta E. It is the change in total energy. So from this problem, we know that 300 joules of energy equals some heat, and we want to know the value of this heat and the direction, so the sign is a positive or negative, and we also know that this is performing 75 joules of expansion work, so this is going to be a negative 75 value because it is work performed by the system. So that means that little basic math, we know that Q is equal to 300 and 75 joules of energy, and this is a positive value. So this is going to be very, very endothermic. That means that heat is going into the system. Okay, this brings us to our very last thing, which is that expansion. So if we are dealing with a gas, gases can expand or contract, and that expansion or contraction can do work. It can perform work. And we do this all the time. That's how the engine in your car works. That's how balloons work. That's a bunch of different ways that you can use expanding gases to perform work of some kind. The equation here is that work equals negative P, which is pressure, times the change in volume. For this equation to give us the unit of joules, work should be pressure should be in units of kilopascals, so kPa, and volume here should be in liters. That being said, atmospheres is a really popular unit, and it's something that you'll see a bunch. So the ways that you can deal with that is you can convert atmospheres to kPa, or you can just use that relationship, and what's hidden under that hint is how to deal with these problems quickly if they're in atmospheres. So the key thing to remember is that there is 101.3 kPa in 1 atmosphere. And since you're more likely to see atmospheres in these problems, you can use that relationship and you know that 101.3 joules equals 1 atmosphere times atmosphere liter. So you'll see that if you were to plug in atmospheres for pressure and liters for volume, you get atmosphere liters. And so one of those equals 101.3 joules. So because of that, we can now solve out this particular problem. As I change my screen here. So a gas is compressed at a constant pressure of 0.08 atmospheres. You notice that it is a constant pressure and is changing from 9 liters to 2 liters. We are compressing this gas, which means we are doing work onto the system instead of the system doing work to its surroundings. So this should be a negative work value. I'm sorry, this should be a positive work value. We are performing it on the system, not the system performing it outwards. So in this case, we have 0.8 ATMs times a change in volume, and that is going to be a change to -7 liters. And this should also be a negative pressure value. So -0.8 times -7 gives us a work value of 5.6 atmosphere liters. And then we can use that relationship between joules and atmosphere liters to go and convert this value into joules. So for every 1 atmosphere liter, there is 101.3 joules of energy. So 5.6 times 101.3, which means the total energy to compress this system is 567.3 joules. So that is just the general basics here. So that covers all of our energy. We'll do some more of this stuff with basically everything in this unit. And if you have any questions, feel free to ask.